Hello, I am Peter Strong, the Chief Architect at Cambium Networks. In this presentation, I will be talking about cnMedusa, the technology used in the PMP450m radio. The presentation is arranged as follows. I will first describe the challenges cnMedusa was intended to address, then give you some insight into how it works. I will follow that with some results showing what it is capable of achieving, and then give you an update on the 450m product. The sustained increase in internet traffic volume is a challenge for many service providers. In the plot on the bottom of this slide, you can see the data throughput at a site over a 1-year period. This data was provided by one of our customers, and it shows an increase of around 3 times over this time. This type of increase is not unusual. Furthermore, for residential service providers, the traffic shows a significant variation through the day. This is shown in the bar graph on the right, where we can see the traffic peaking around 9 p.m. This evening peak in traffic is driven by the increasing use of video on-demand services by an increasing proportion of internet users. Operators tell us that around 70% of peak time traffic is associated with these applications. The individual load per video stream is modest. 2 megabits a second is enough for standard definition TV. Many users expect to use these services within the existing data plans. After all, if I have a 5 megabit plan, that should be enough for one standard definition video stream. The problem for service providers is that the video load is continuous, often tens of minutes or hours. So the opportunity for oversubscription diminishes. So while the data link to an individual subscriber is easily able to cope with the traffic, congestion occurs in the point-to-multipoint access layer. There is not enough spectrum and airtime for the access point to deliver data to all the active users. Operators are addressing this challenge by densification and resectorization with frequency replanning, but there's only a finite amount of spectrum available and tower sites available. As a result, interference levels are rising, reducing throughputs achieved on individual links. The challenge is how to deliver the rising volumes of internet data in an affordable way. cnMedusa was developed to address these challenges. It is an advanced beam management technology building on Cambium's considerable experience in fixed wireless access. Combining innovations in scheduler algorithms, antenna technology, and RF and digital signal processing, it maximizes throughputs under all wireless and traffic conditions. It is an affordable technology optimized for line-of-sight and near line-of-sight fixed deployments in unlicensed and lightly licensed spectrum. And the 450m is the first product to use this technology, enhancing the capability of the PMP450 platform. cnMedusa comprises 4 components. The first is the flexible transmission modes. There are 3 types of transmission mode. The sector mode, which is used for broadcast transmissions. The single-user MIMO mode, which is used for beamformed transmissions to a single user. And the multi-user MIMO mode, which, as the name suggests, is used to communicate simultaneously with multiple users. Each of these 3 types have a downlink and an uplink variant, and these modes can be applied flexibly on a per OFDM symbol basis. A given OFDM symbol could be a broadcast transmission, and the following could be a multi-user MIMO transmission. The transmission mode transition occurs in the cyclic prefix of the normal OFDM transmission. There is no incremental overhead associated with the mode change. The second component is the precise ERRP control. This is performed to ensure the link budget is maximized independent of the transmission mode. Algorithms predict the maximum ERRP for each beamformed and adjust the TX power to ensure it complies with the regulatory limits. This is achieved with a cable-free integrated antenna and calibrated transmit feedback loops, which maintain phase and power alignment between the RF chains. The third component of cnMedusa is the low latency scheduler. The scheduler determines which queues and transmission modes will be used for each OFDM symbol, responding in a TDD cycle to changing traffic and wireless conditions. The high-resolution sounding is the fourth component of cnMedusa. With MIMO, a high-resolution channel estimate is required at the access point to enable high QAM modulation modes. In cnMedusa, this is delivered with a noise-tolerant, low-overhead mechanism. Spatial division multiple access is the MIMO's technique that enables cnMedusa to achieve a significant increase in spectral efficiency. In SDMA, separate radio beams send different data to different users at the same time in the same spectrum. To do this, it is important that the different beams do not interfere with each other. This requires precise knowledge of the current radio channel state of each user for the multi-user beamforming. It also requires that the different users participating in the transmission have sufficiently distinct spatial signatures. In cnMedusa, the collection of users participating in a multi-user transmission is called a group. The scheduler forms new groups each TDD cycle in response to changing wireless and queue conditions. The minimum azimuth spacing between members in a group is between 4 and 7 degrees, depending on the group size and the radio frequency. The graphic illustrates a sector with multiple users. Two groups are shown, one in red and the other in green, each with 4 users. These two groups could be used on consecutive TD cycles. The spatial multiplexing gain indicates the increase in delivered rate compared to a non-MIMO system. It depends on, among other things, the number of users in the group. This will vary depending on the spatial distribution of the active users, i.e. the users requiring service at a given time. If all users are in the same direction, then there's no opportunity for multi-user transmissions. In practice, under loaded conditions with typical subscriber distributions, we see up to 3 times increase in the throughput compared to a non-MIMO access point, serving the same subscribers in the same RF channel. The PMP450m was specifically designed to address the traffic load created by services like video on demand. With MIMO, it provides a step increase in capacity of congestion-limited sectors, and it does this without requiring new spectrum. To complement the higher wireless capacity, the performance of the bridging engine has been enhanced, achieving higher PPS, and enables an increased number of subscribers per access point. The upgrade of a 450 sector is simple. It involves replacing the access point with a 450m access point. The 450m supports a peak of 14 spatial streams comprising 7 users, each with 2 streams. It's this high peak rate which maximizes the average spatial multiplexing gain. The headline capability of 450m is impressive. Our hardware and software development process requires frequent radiative tests in an anechoic chamber, such as the one shown in the photograph. The radiated testing is considered representative of the RF propagation environment in the vicinity of an access point mounted on a tower free of local obstructions. In this testing, the PMP450m achieves greater than 1.2 gigabits per second sector throughput in a 40 megahertz channel with a downlink-only data stream. Even with downlink TCP testing, which has a significant uplink packet rate, the 450m achieves greater than 550 megabits a second in a 20 megahertz channel. We recently performed TCP speed testing on a live customer sector. The purpose was to explore the spare throughput capacity of the sector. The sector had a PMP450 SMs and had the AP upgraded to a PMP450m. The sector was configured for a channel bandwidth of 30 MHz and a 75% downlink utilization. It had about 150 registered subscribers. We developed a TCP speed test tool running on a Raspberry Pi, which contacts a server every hour and conducts a TCP speed test. Working with the service provider, we arranged to install the speed test Raspberry Pis into 6 subscriber homes, all receiving service from the sector. Each Raspberry Pi was installed behind the subscriber's home router, and it contacted our server located on the internet. Simultaneous speed tests were performed 5 minutes after the hour. The TCP speed tests were normally 10 seconds in duration, although those performed in the early hours of the morning were extended to 20 seconds in duration. Each Raspberry Pi established a single TCP session, and the server offered data as fast as the client would accept it. The subscribers associated with the speed test were capped at a 33 megabits down and 3 megabit up limit according to the operator's plan. Diagnostic data was collected from the PMP450m serving the sector. This allowed us to determine the aggregate delivered downlink data for each TDD cycle. This is shown as a data rate versus time centered on each speed test in the bottom left-hand plot. Each line gives a result for one speed test. As the left and right-hand sides of the plot, on the left and right-hand side of the plot are the data rates due to the normal traffic delivered by the access point. Here we see values distributed between 0 and 200 megabits a second. We also see the step in delivered data rate starting around about time 55 seconds, and this is due to the simultaneous TCP speed test. This is sustained for 10 or 20 seconds and then drops to the normal rate. In the lower right plot, the same raw data is presented in a slightly different way. Here we average the results in 6 4-hourly intervals during the day. The darker blue line is the average for midnight to 4 a.m., red is 4 a.m. to 8 a.m., etc. At the left and right-hand sides of the plot, we see the data rates for the normal traffic, showing the expected variation according to the time of the day, peaking at 90 megabits per second for the 4 p.m. to midnight intervals. For each interval during the day, there is a significant step in throughput when the speed test is run, suggesting significant spare capacity in the sector. In fact, the spare capacity is higher than shown because the speed test subscribers were subject to the data rate cap as well. The PMP450m has been shipping for just under 2 years. It is currently providing service in around 5,000 sectors and is being selected for sector upgrades as well as greenfield PMP450 deployments. There is a solid development roadmap behind the 450m. It was originally released supporting up to 20 MHz channel bandwidths. Subsequently, support for 30 and 40 MHz channels was added, and in the next few months we will add uplink MIMO and deliver a 3.5 GHz version. There are 2 significant use cases targeted for PMP450m. The first is the use case I've been focusing on, which is the provision of service to oversubscribed residential users, optimized for the delivery of streamed media. This traffic is dominated by video-on-demand services, in which encrypted unicast traffic is the main protocol used to deliver this data. MIMO delivers this data very efficiently, opportunistically exploiting the unicast nature of the traffic and the spatial distribution of a large number of active subscribers. The second use case is high-capacity point-to-few-point, and we see this with a smaller number of our current customers. In this case, There is a small number of remote terminals. The location of these and the access point are engineered to maximize the capacity of the access network. Capacity predictions for users in these known locations can be performed with tools such as Cambium's Link Planner. I hope this presentation has been useful to you. If you would like more information, please visit our website at cambiumnetworks.com. Thank you.